Welcome, physics enthusiasts, to an exhilarating showdown of energy transformations. In this electrifying video, we will dive into 5 numerical problems that demonstrate the fascinating interconversion between kinetic and potential energy. Get ready to witness the dynamic dance of energy as we unravel the secrets of physics. Don't forget to hit that subscribe button to join our viral physics community. Let the energy transformation begin. Problem 1, from rest to motion, kinetic energy unleashed. A 2 kilograms object is dropped from a height of 10 meters. Calculate the kinetic energy possessed by the object just before it hits the ground. Given mass of the object, m, equals 2 kilograms. Height from which it is dropped, h, equals 10 meters. Acceleration due to gravity, g, equals 9.8 meters/s squared. Potential energy at the height, P, equals m times g times h. P equals 2 kilograms times 9.8 meters/s squared times 10 meters equals 196 joule. Since there is no initial velocity, all the potential energy is converted into kinetic energy just before hitting the ground. Kinetic energy, K, equals P. K equals 196 joule. The kinetic energy possessed by the object just before hitting the ground is 196 joules. Problem 2, from motion to height, potential energy ascends. A car with a mass of 1,000 kilograms is moving at a velocity of 20 meters per second. Calculate the height it can climb, assuming all its kinetic energy is converted into potential energy. Given mass of the car, m, equals 1,000 kilograms. Velocity of the car, v, equals 20 meters per second. Acceleration due to gravity, g, equals 9.8 meters/s squared. Kinetic energy, k, equals half times m times v squared. K equals half times 1,000 times 20 squared equals 200,000 joule. Potential energy, P, equals K. P equals 200,000 joule. Using the formula for potential energy, we can calculate the height, h. P equals m times g times h. 200,000 equals 1,000 times 9.8 times h. H equals 20.41 meter. Problem 3, bouncing energy, interplay of potential and kinetic energy. A ball weighing half a kilogram is dropped from a height of 2 meters. Upon hitting the ground, it rebounds to a height of 1.5 meters. Calculate the loss of mechanical energy during the bounce. Given mass of the ball, m, equals half a kilogram. Initial height, h1, equals 2 meters. Final height, h2, equals 1.5 meters. Acceleration due to gravity, g, equals 9.8 meters/s squared. Initial potential energy, P1, equals m times g times h1. P1 equals half a kilogram times 9.8 meters/s squared times 2 meters equals 9.8 j. Final potential energy, P2, equals m times g times h2. P2 equals half a kilogram 9.8 meters/s squared times 1.5 meters equals 7.35 j. The loss of mechanical energy during the bounce is the difference between initial and final potential energies. Loss of mechanical energy equals P1, P2. Loss of mechanical energy equals 9.8 j, 7.35 j equals 2.45 j. During the bounce, there is a loss of 2.45 joules of mechanical energy. Problem 4, roller coaster thrills, the pendulum swing. A roller coaster car, with a mass of 500 kilograms, reaches its highest point on a loop-the-loop track. At this point, it has a speed of 10 meters per second. Calculate the radius of the loop-the-loop, assuming all its kinetic energy is converted into potential energy at the top. Given mass of the roller coaster car, m, equals 500 kilograms. Velocity at the highest point, v, equals 10 meters per second. Acceleration due to gravity, g, equals 10 meters/s squared. Kinetic energy, k, equals half, times m times v squared. K equals half, times 500 kilograms times 10 meters per second squared equals 25,000 joule. All the kinetic energy is converted into potential energy at the highest point of the loop. Potential energy, P, equals K. P equals 25,000 J. Using the formula for potential energy in a vertical circular motion, we can calculate the radius, r. P equals m times g times 2r. 25,000 J equals 500 kilograms times 10 meters/s squared times 2r. R equals 2.5 meters. The radius of the loop is 2.5 meters when all the kinetic energy is converted into potential energy at the top. Problem 5, the catapult launch, harnessing potential and kinetic energy. A catapult launches a projectile with a mass of 2 kilograms. The projectile reaches a maximum height of 20 meters. Calculate the initial velocity at which the projectile was launched. Given mass of the projectile, m, equals 2 kilograms. Maximum height reached, h, equals 20 meters. Acceleration due to gravity, g, equals 9.8 meters/s squared. Potential energy at the maximum height, P, equals m times g times h. P equals 2 kilograms times 9.8 meters/s squared times 20 meters equals 392 joule. All the potential energy is converted into kinetic energy at the highest point. Kinetic energy, K, equals P. K equals 392 joule. Using the formula for kinetic energy, we can calculate the initial velocity, v. K equals half, times m times v squared. 392 J equals half, times 2 kilograms times v squared. V squared equals 392 J, 1 kilogram. V squared equals 392 square meters/s squared. V equals 19.8 meters per second. The projectile was launched with an approximate initial velocity of 19.8 meters per second. Congratulations on experiencing the electrifying world of energy interconversion through these mind-boggling numerical problems. We hope you were captivated by the dynamic dance between potential energy and kinetic energy. If you found this video helpful, don't forget like and share it with your fellow physics enthusiasts.